Stripping down science. The Naked Scientists.
Hello, it's Sunday the 19th of June. Welcome to The Naked Scientists with me, Ben Valsler.
And me, Dave Ansell.
This week, creating gas from coal and capturing carbon. We're exploring two technologies, one that can make the most of an otherwise useless coal seam, and another that can capture carbon dioxide and turn it into useful products.
And I investigate one of the most important historical uses of coal as a fuel for steam engines.
In the news, how dinosaurs inspire new designs for aircraft, designing unique chemistry, and spotting a star being ripped apart by a black hole.
Plus we'll be hearing about the South African bid for the Square Kilometre Array, the largest radio telescope that's ever been planned.
So if you have any questions for us, then get in touch now. You can tweet at Naked Scientists, write on our Facebook page, you can find that at thenakedscientists.com/Facebook, or drop us an email. Our email address is chris@thenakedscientists.com.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
This is The Naked Scientists with me, Ben Valsler, and with Dave Ansell. And we begin with a look at some of this week's top science stories. A unique astronomical event, an incredibly bright and long-lived burst of gamma rays, was probably the result of a black hole destroying a star, according to research published in the journal Science this week. On the 28th of March this year, NASA's SWIFT satellite observed a bright flash of gamma rays emanating from a distant galaxy around 3.8 billion light-years away. Gamma ray bursts like this are associated with some of the most energetic and destructive events in our universe, such as the supernova and collapse of a massive star down into a black hole or into a neutron star. This flash, which is now known by the catchy name of SW1644+57, was quite unusual. Normal gamma-ray bursts are very intense but very short-lived, and they're followed by an afterglow of lower-intensity emission. This event, though, continued for weeks, outlasting any previous known burst, and rather than fading away quietly, it was followed by a number of less intense bursts of radiation, almost like an earthquake and its aftershocks. To determine exactly what caused this unique event, it was vital to determine whereabouts in the galaxy it had occurred. Andrew Levan and colleagues at Warwick University used subsequent observations taken by the Hubble Space Telescope and the Chandra X-ray Observatory to confirm that the event had taken place at the heart of the galaxy. This left one logical conclusion as to the cause of the event, that they had witnessed a star about the size of our Sun being torn apart by a massive black hole. The enormous gravitational pull of a black hole at least 1,000,000 times the mass of the Sun would cause the star to initially distort into a banana shape before being ripped into a ring of material that would then rain down onto the black hole itself. Spinning black holes tend to radiate this energy away in two highly collimated beams, one from each pole, and this time the Earth just happened to fall right in the firing line of one of these beams. Dr. Levan now hopes to look at historical data to find evidence of what we call off-axis events, where we're not in the firing line, and this should give us an idea of how rare these extraordinary events really are.
That sounds like an absolutely incredibly violent event.
Well, these gamma-ray bursts are some of the brightest, some of the most intense things we see in the universe. And things like a supernova, as we know, it's an incredibly destructive event. You also get things called blazars, which come from what are called active galactic nuclei. Now, this is usually where there's material raining in onto a black hole, and it gets so heated up by this process that it gives out lots of radiation. But this is really in a class of its own, because it's not just the effect of material raining into a black hole, but it's tearing a star apart.
Brilliant. Well, my story this week is again about astronomical fireworks, but rather close to home. Comets. Now, comets are small astronomical bodies that mostly travel into our solar system from the far reaches of it. And as they move close to the sun, they heat up evaporating volatiles like carbon dioxide and water, and these then recondense and form this characteristic tail. They're actually quite difficult to study because although their tails can be enormous and you can actually see them with the naked eye, the actual comet is relatively small, only a few kilometres across. When they're close to us, of course, they're surrounded by a cloud of particles which form their tail, which is a bit like trying to see them through a mist. There have been a couple of missions to comets in the past, and the most recent was the NASA Deep Impact mission, which first visited the comet Tempel 1 in 2005, but as a bonus extra mission, because they had a bit of fuel left over, visited the relatively small and unpredictable comet Hartley 2. And this is a slightly unusual comet in that it's spinning in an unusual way. It's not just spinning about one axis, it's spinning about two, which indicates that there's something odd going on with it. It's also quite active. And so the mission went through and they've just finished analysing a large chunk of the data. They've found that the comet looks like a giant kilometre-long dumbbell, and the jets of gas are coming out of the ends, which is slightly odd to start with. The small end at the moment is slightly more active than the big end. And the amount of water compared to carbon dioxide appears to be lower at the small end than the big end. So this might very interestingly indicate that the comet wasn't uniform when it was created. Or it might indicate some interesting processes after that. But certainly if that was the first one, that says something really quite deep about comets, and they're not quite as simple as we thought they were originally. They also saw a very pristine white ring around the middle of the dumbbell, which indicates there's no dust on there. It's quite a new surface, and they think it's been created by stuff being thrown out from the ends, being trapped by the tiny amount of gravity on the comet, and sort of redepositing in the middle. So this indicates that comets might be more active and varied than they thought before.
There's still a lot to learn, isn't there, about the structure and the evolution of comets. The Deep Impact mission you mentioned earlier, what they actually did was crash something into a comet to try and throw up bits of the surface and see not only what actually comes out, but then subsequently see how that wound, as it were, heals, or if it heals at all, or if it just stays as this permanent crater.
And also see actually what's in the surface, because normally what evaporates is stuff which evaporates, and so if you smash something into it, you actually get a model, a picture of what's actually in there rather than what just happens to get kicked out naturally.
So the iconic nickname of comets as being a dirty snowball actually doesn't really tell you quite how complicated they are.
Indeed.
Now, the Square Kilometre Array, or the SKA, is set to be a groundbreaking new radio telescope operating at a wide range of frequencies with as much as 50 times more sensitivity than any existing telescope of its kind. It should help us to answer some of the really big outstanding questions about our universe. Now, the headquarters will be based at the Jodrell Bank Observatory in Cheshire, but the telescope itself is either going to be located in Australia or in South Africa. This week, Bernie Faneroff, the project manager for the South African SKA bid, visited London and met up with our own Chris Smith.
It'll be made up of two different kinds of what are called receptors. Most people will know what a satellite dish looks like. A satellite dish is really a mirror. It focuses radio waves from space onto a radio receiver. There'll be another kind of receptor, which is more like a fisheye lens. It sits on the ground. You don't steer it physically, you steer it electronically, but it sees almost all of the sky all the time. So the Square Kilometre Array will be made up of a couple of thousand dishes and 1,000 or so of these fisheye lenses. And the dishes will be spread out over about 3,000 kilometres, the fisheye lenses over a couple of 100 kilometres. They'll all be joined together with optical fibre, so they all look at the same thing at the same time. You feed the signals from all of these dishes and fisheye lenses together into one central computer, and you can process the data to make a picture of whatever it was that they were looking at.
That must be one mega computer.
Well, the estimates are that you'd have to have a computer running at exaflop speeds. Exaflop speeds is of the order of 1,000 times faster than the fastest supercomputers now. The data transport would be several hundred terabits per second, so you're looking at a couple of 100 times more data traffic than you have through the entire World Wide Web at the present time. So it pushes a lot of different technological boundaries.
So why South Africa?
Well, first of all, we have an exceptionally good site. It's very quiet, radio quiet, in the sense that there's very little interference. We've been able to work with our signal broadcasters and our mobile phone operators and others to reduce even further any signals that there are. So it's a very quiet site. The physical characteristics are good. We have large flat areas. Temperatures and winds are benign. There's no extreme weather. And there's a lot of infrastructure already in place, so it's easy to put it down there. And it reduces the costs because the cost of construction is lower. You've got some infrastructure, but also building in South Africa is just more affordable than it would be in many other places.
Is South Africa ready for this kind of project, though? Because to develop that kind of computer and that kind of infrastructure, can the country deliver that at the moment?
Well, we certainly can. First of all, we've got quite a good base of high-tech industry as well as construction and engineering industry with an international track record. But we've done two things which have helped us to develop a really vibrant and world-class community. The first one is that we've been building what we call the Meerkat telescope, which is a scaled-down version of the square kilometre array. It will have 64 dishes instead of a couple of thousand of them. It'll be on the same site in the Karoo. We built the first 7 dishes and we're commissioning that as a prototype. Then going with that, we've developed a big bursary and grants program to strengthen our universities. So we have 5 research chairs in our universities. We've had 117 PhD and MSc students in engineering and astronomy. We've got about 100 undergraduates in physics and engineering. We're training technicians and artisans. One of the things which has become clear is that the 100 or so young engineers and scientists who directly work on the project now, I'm excluding the ones in the university, are amongst the best engineers and scientists in the world, and that has been recognised by the rest of the SKA International Consortium.
And if it does go South Africa's way, what will this mean to the country if you get this?
I think it'll be very important for us. First of all, it'll change the way we see ourselves, that we can be a centre for science and astronomy. And one of government's objectives from 1996 is for Southern Africa to be a centre of astronomy. The other thing is I think it'll change the way the world sees us. We're already seeing a lot of very good academics and researchers wanting to come to South Africa to work on the Meerkat. And that wasn't so easy a few years back. If we have the SKA in Africa, we'll have more of those people coming, and that will strengthen our innovation system, our universities, and it will just strengthen the whole capability in these high-tech and scientific areas.
And what are the really big questions that you're going to answer with this?
The first one, I think, is that people would like to understand dark energy better. Why is the universe expanding faster and faster? What is the large-scale structure of the universe? It has voids in it, bubbles. How do the bubbles originate? What has happened to the structure of the universe over the life of the universe? It will enable us to study galaxies and how galaxies form and evolve so that we can understand better what dark matter is. Both dark energy and dark matter are known to be there because we can see their effects, but we don't know what they are. So those are very interesting challenges. Then it will test Einstein's theory of gravitation by enabling us to look for gravitational waves, by enabling us to study what happens very close to black holes. It'll look for protoplanets. These are all very exciting questions.
Bernie Fanneroff talking to Chris Smith at the South African High Commission this week. Regardless which country, the SKA is planned to start construction in 2016 and should be fully operational by 2024. So it'll be very exciting to see if that happens, and if it does, the results that they start getting. Porous molecules, which are useful in a range of applications including separating chemicals and catalysing reactions, may be designed on demand thanks to a new method published in the journal Nature this week. Molecules which have well-defined porosity and well-understood activity, now this includes zeolites and things called metal organic frameworks or MOFs, play important roles in many different chemical processes. MOFs have been touted as a safe solution to hydrogen storage due to their ability to absorb enormous amounts of gas on their surfaces, but they're also useful in water purification and as molecular traps in order to allow us to study molecules. But their production, when we make them, it often distributes the functionality fairly randomly between the pores, and this places an upper limit on their use. Professor Andrew Cooper at the University of Liverpool, working with groups at University College London and Cambridge University, has developed a method for modelling nanoporous molecular frameworks with atomic precision and then producing them from modular components. So almost like Lego, in a way. Cooper and colleagues use a lock and key assembly technique, mixing porous organic cage molecules and then allowing them to self-assemble. They can accurately model and predict how these molecular modules will mix, meaning specific functionality can be computer designed. One of the advantages of this technique is that the molecules are soluble. Now, this means that once the constituent pore modules are synthesized, researchers need only mix up these modules in a solution, allow them to just build themselves to self-assemble, and then they remove the solvent and you have your porous molecule. The researchers have put their method to the test and they have produced 4 bespoke molecular cages, and they've confirmed their structure experimentally. And this, they say, opens the way for in silico production of structure and properties for new candidate porous materials based solely on 2-dimensional chemical sketches. And this allows design by computational selection.
So this would mean that you could put a catalytic site at some point in your pores and then enhance the catalytic effect. You could have a huge surface area, and every little pore would have the little bit of catalyst or a little bit of reactant in there, and you'd have a very efficient system.
Well, and also it means that you can control where the functional bits, so where your catalyst is within the pore, and that in turn may allow you to more precisely control that catalysis and more precisely control the way that, say, these materials actually filter different molecules. It's slightly complicated stuff, but actually the range of applications are enormous. It's very exciting.
Fascinating. Now for something slightly different. Ancient reptiles are inspiring aircraft designers. Now, although for most large aircraft and airliners, being able to change direction very quickly isn't hugely important, otherwise everyone throws up. As unmanned aerial vehicles are getting used more and more, especially in complex urban environments, being able to turn sharply can make a difference between carrying on your mission or ending up splattered against a wall. A very productive seam of ideas for engineers in the past has been biomimetics, copying ideas from living things. This has given us a range of ideas ranging from Velcro to cat's eyes in the road. But Brian Roberts and Rick Lind from the University of Florida have been taking this strategy one step further. They've been taking ideas from dead creatures, very dead creatures that haven't lived for 65 million years, pterosaurs to be precise. These were a form of flying reptiles which survived for over 150 million years and included the largest flying animal so far found, which had a wingspan of 40 feet. One striking feature of many of these pterosaurs is that they have large head crests. It's been suggested that these were just for display, but maybe they had some kind of aerodynamic purpose. They look very much like a rudder. So the group wondered if putting a rudder at the front of the plane might be useful. They've done lots of modelling and found that for the same size of rudder at the front of the plane, it should give the plane a 15% smaller turning circle. The problem is you also lose a lot of stability, so they're looking at somehow morphing the rudder or possibly moving it from front to the back to get the best of both worlds. So in the future we may see pterosaur-inspired planes flying around our cities, and who knows what else ancient animals and plants might inspire.
It's fascinating that this has been inspired by these iconic creatures that you always see in any diorama of dinosaurs. You always see them up in the sky. But has nobody tried this before just by trial and error, just moving the rudder to the front to see what happens?
I guess the big problem is the stability, that if the rudder's at the back, it automatically means the plane carries on pointing in roughly the right direction. But if something goes slightly wrong at the front, you need then it will suddenly make a sharp corner. So you want to have some kind of feedback system or some cunning control system or this morphing idea to take advantages of it without getting all the disadvantages.
I wonder if it could also be included in the, again, biomimetic designs we see of flapping aircraft, because rather than just an aeroplane that's remote controlled, if we have these flapping aircraft that also have this front-mounted rudder, that could give us even more degrees of freedom.
Yes, although one of the reasons making flapping aircraft is that they look like birds, so you can spy on people. I think looking like pterodactyls on pterosaurs might not have quite the same advantage.
It might be a little bit frightening, I'd imagine, compared to seeing what looks like a seagull.
Yes.
And if you would like to follow up on any of the stories that we've covered this week, you can find more information and references online at thenakedscientist.com/news.
Laying the facts bare. The Naked Scientists. Look us up online at nakedscientists.com.
This is The Naked Scientists with me, Ben Valsler, and with Dave Ansell. Still to come, we'll find out how to extract a useful gas fuel from hard-to-access coal and how to turn waste carbon dioxide into valuable chemicals.
But now, in the late 1940s, a chemist called Willard Libby, who'd originally worked on uranium during the Manhattan Project, developed a method of dating material with a biological origin. As it's radioactive, the levels of carbon-14 in the material decrease as it ages, but the amount of stable carbon-12 doesn't change. Therefore, by looking at the ratio of carbon-12 and radioactive carbon-14, he could date the material. Today, radiocarbon dating, as it's called, is an extremely accurate and useful tool to date an archaeological find that contains any previously living material. Planet Earth podcast presenter Sue Nelson met Tom Hyam from the Oxford Radiocarbon Accelerator Unit to find out how it works.
This machine, its job is basically to take tiny amounts of graphite which contain the carbon and therefore the carbon-14 that derive from the archaeological bone or charcoal or whatever it happens to be, and to separate from all of the other interfering particles just the carbon-14. So this is rather like a large sieve. And the way it does that is by particle acceleration, by beam bending the particles so that they can be separated by magnetic forces. The problem that we have, though, is that a tiny amount of that carbon is carbon-14. One particle in a billion is carbon-14. So that's why we need such a large machine to be able to separate all of the interfering particles that aren't carbon-14 from carbon-14.
So if you had a bone, for example, that you wanted to analyse, where would it actually go?
The first stage is to take the bone, to take about half a teaspoon of powder from the bone, and to extract the collagen from that bone. Stage 2 is then to combust the collagen, purify the gas, and convert the carbon dioxide into graphite. And then the graphite is then loaded into one of those small aluminium holders there.
This almost looks like a gun canister with bullets.
Yeah, and then you see this little hole on the top. It's about a millimetre in circumference. That contains the graphite from the bone, and it's pressed very firmly onto the top of this target. And then it's put into this large wheel of samples here, which number about 50 or 60. And once the accelerator is loaded with this wheel, a cesium beam is projected onto the surface of the graphite. And that process, called sputtering, gives a charge to the particles. And that is really, really important, because if we don't give the particles a charge, that means we can't bend them, we can't move their trajectory and separate the particles from other particles of a different mass.
Let's go into the quieter area now.
This is the control room where the measurements are monitored and the machine is started, stopped, and also where the dates are calculated. In the old days, it used to take a day or so to calculate a batch of radiocarbon dates. But now, of course, we have computers that do it in the space of a blink of an eye.
How do you actually tell the age of something from the amount of radioactive carbon in it?
The dating process is built around the half-life of radiocarbon. The half-life simply means the amount of time it takes for half of the radioactive carbon that is present per gram of material in a living organism to decay after death and disappear. So we know that the half-life of radiocarbon is about 5,500 years. That means that every 5,500 years the amount of radiocarbon declines by half. So after 10 half-lives, you're back to around 55,000 years, and then there should be no more carbon-14 left. So that marks the limit of the dating technique. The great thing about radiocarbon dating is that carbon is ubiquitous in the biosphere, so there are many different types of material that we could date, whether they be bones, charcoal, wood, to things like mollusks and fish bones, pollen. Since the 1950s, there's been a doubling of the amount of radiocarbon in the world because of the nuclear testing that took place in the 1940s and 50s and 60s. So if we measure something that's modern being since 1950, we can get a very high level of radioactive carbon that we know, therefore, must equate with a date in the modern period.
Modern particle accelerators and pre-treating samples to remove contaminants have improved the accuracy of radiocarbon dating. In some cases, artefacts need to be retested, and Tom's unit helped produce recent research which suggested that Neanderthals probably died out 10,000 years earlier than previously thought.
Unfortunately, in many cases, when we do this work, we find that the previous states are underestimating the real age. So there's a huge amount of work to be done still in applying these new techniques to find the real chronological picture.
So you could actually put a lot of noses out of joint.
Yeah, that's right. I think it's fair to say that there are a lot of people with a lot of vested interests in this, and they've written a lot over the last few decades, and they've been involved in bitter arguments that in some cases are over data that we now know is probably not reliable. So yes, there is a tendency to do that.
That was Tom Hyam from the Oxford Radiocarbon Accelerator Unit talking to Sue Nelson. You can find out more about Planet Earth resources online at thenakedscientist.com/Planet Earth.
This is The Naked Scientists with Ben Valsler and with Dave Ansell. Still to come, we'll find out how to capture carbon from power station exhaust fumes and turn it into something that you can sell. Keep your questions coming in. Tweet at Naked Scientists, right on our Facebook page. That's at thenakedscientists.com/Facebook, or drop us an email. Our email address is chris@thenakedscientists.com.
But first, underground coal gasification is a way to get useful fuel from otherwise inaccessible coal seams that are simply uneconomical to mine. To explain more, we're joined by Professor Dermot Roddy from the University of Newcastle. Now, Dermot, what actually is underground coal gasification?
The easiest way of thinking about it is to remember that for the last 30 years we've been used to bringing natural gas into our homes from the North Sea. But before that, the gas used to come from the local gas works. And there you would gasify coal to turn it into a mixture of hydrogen and carbon monoxide. And that's what we brought into our homes. With underground coal gasification, the difference is you don't have to mine that coal before you gasify it. So you're injecting oxygen and steam into the coal while it's still in the coal seam.
So if you're injecting oxygen and steam, there's some chemical reaction going on underground to turn it into a gas?
That's right. It's the same reaction that would have happened in a gasworks. So the idea is you drill down into the ground, maybe 800 metres or more underground, and then you can deviate the drill, turn it through an angle, and follow that coal seam as far as you want. And then you drill a larger hole down to meet it. And when you inject oxygen and steam into that maybe 8 centimetre diameter hole, you start to gasify the coal, and you bring that gas, that synthesis gas, up to the surface.
So what do you use this synthesis gas or syngas for?
Well, some people will use it for generating electricity, because you can use it in much the same way as you would use natural gas in a combined cycle gas turbine. Or you can use it, as has been done for many years in South Africa, for synthesising fuels, petrol and diesel and so on. Or if you want to, and we tend to do this up here in the northeast, you can use synthesis gas to make chemicals, polymers and so on.
And I guess you get at coal seams you couldn't do otherwise because they're too small or in too awkward places?
Well, that's right. We're particularly interested in deep seams because you want to go down well below the top of the water table, down to the point where you're into permanently unusable water. So you're deliberately going very deep underground. In the UK, for example, it was very unusual to go down below, say, 250 metres, whereas here we're saying we want to go down at least 800 metres. And you can certainly get into very thin coal seams. But what that means in practical terms is, whereas in the past a respectable coal mine might have produced 1 or 2 million tonnes of coal per year, the UK has got about 50,000 million tonnes of coal that nobody has any intention of ever mining. So that's the size of the venture. It's not just the odd little coal seam here or there that you might want to do this with. You're talking about 1,000 years worth of electricity generation or something like that from coal that today people wouldn't think of mining.
So if you're pumping steam down these pipes, I guess this reaction is got to be quite hot to happen. Does this mean there's a kind of energy penalty involved in converting the coal from a solid into the gas?
Well, one way of looking at it is if you didn't do this, all of the energy would remain underground and you would never get to use it. I think what you end up doing is that you want to liberate as much of the energy that's in the coal you want to bring as much of the energy that's in the coal up to the surface. If you just burn coal, you release all of the energy. And the whole point in a gas works or in underground coal gasification is you partially combust this material so that actually most of the energy is still in the gas when you bring it to the surface. That's the whole point. Because then you're saying this gas is a source of energy. I haven't actually used up very much of the energy in this partial combustion reaction that turns coal into hydrogen and carbon monoxide.
I guess just mining conventional coal is actually quite an energy-intensive process. How does this compare with a conventional mine?
There's very little experience of actually mining at these kinds of depths. I think the other thing you find with mining at these kind of depths is incredibly dangerous. You look at the death rates that people are accepting now for deep mining in Russia and China and so on, and you really wouldn't count on us doing that in Europe. I think from an energy point of view, you expect that about 80% or 85% of the energy that's in the coal now will end up coming to the surface, and the rest you lose.
Okay, so this is actually quite a useful technology. Are there
yes.
any environmental impacts other than just the fact, I guess, you're burning coal, which is not ideal in terms of carbon dioxide?
Well, from my point of view, I would say that if you want to do this in the UK or in Europe, you absolutely must have a carbon management plan, or nobody is going to allow you to do it, nor should they, actually, in my opinion. So when people talk about carbon capture and storage as a technology that should be used on all coal-fired power generation, my view would be the exact same applies with underground coal gasification. So it should only really be used in conjunction with some kind of a carbon management plan. You have to capture the carbon dioxide. In a sense, it's like integrated gasification combined cycle technology, where you capture the carbon dioxide first before you put the hydrogen-rich gas through your gas turbines. Then once you've captured it, you do something with it. You can put it in a pipeline, and people write extensively about that. We're working on technology that would allow you to put the carbon dioxide back into the void you've just created in the coal seam. And there are yet other people who would say, I've got clever ways of using carbon dioxide as a chemical feedstock. But in a UK context or a European context, it's UCG, underground coal gasification, is a complete non-starter unless you've actually got a carbon management plan.
Brilliant. Thank you very much, Dermot Roddy from the St Joseph Swan Institute for Energy at Newcastle University.
Now, as Professor Roddy was just saying, as long as we continue to burn fossil fuels, we'll want to try and recapture the carbon that would otherwise escape into the atmosphere. There are a number of different ways to do this, all with their own advantages and, of course, disadvantages. But we are joined by Joe Jones, who's from Skyonic in Texas, and they've developed what they call a sky mine, a system that not only extracts CO2, but actually turns it into something that they can sell. Thank you ever so much for joining us, Joe.
It's a pleasure.
How does the sky mine actually work?
Well, Skyonic Corporation has been working for 6 years on a sky mine process to capture carbon dioxide from flue gas and convert it into solid carbonate and bicarbonate minerals. And we do that by exploiting an ionic chemical property of carbon dioxide. Namely, it's an acid gas that forms weak carbonic acid when it's dissolved in water. We combine that weak acid with a strong base to form a neutral salt, just like you may have done in your high school chemistry laboratories. And we can make sodium carbonate, sodium, which is the washing soda that's used in detergents, sodium bicarbonate, the edible salt that can soothe your stomach, or make calcium or magnesium carbonates that form limestone or dolomites, or precipitated calcium carbonate that makes up 40% of white paper and other things.
So with the limestone versions and the precipitates and so on, that's a very good way to capture carbon that you can then, say, bury in the ground again, a good way for storage. But with the other products, there's a market for those, isn't there? You can actually sell the result of recycling this waste.
Indeed. In the sodium carbonates and bicarbonates market, there's a little over $10 billion of chemical product that is currently either mined from archaeocarbon, which is releasing ancient sequestered CO2, or is made by synthesis techniques that use a great deal more energy and thereby generate more carbon footprint as well.
So where does the alkali, where does the base that you react it with, where does that come from? Does that have to be mined? Is it an expensive process to produce it in the first place?
Well, sadly, there are no base mines that are available, so you have to synthesize it from salt and water itself. If you take salt water and energy, either in the form of electricity for electrolysis or electrolytic means, or using heat energy in thermolytic means, you can force the neutral salt, in that case, to split itself into hydrochloric acid and a very usable base.
And so there's obviously an energy cost in order to do the electrolysis in the first place. But I think there is an energy cost for all of the different carbon capture mechanisms we have. In fact, I think at the absolute least you need to increase the output of your power station by 20%. And I think some of them, it's as far as 90%. You're almost doubling the amount of energy you need to produce in the first place just to capture back the carbon. How efficient is the SkyMine? How much extra energy do you need?
The SkyMine does have positive engineering leverage, so that it does sequester more carbon dioxide than its operation generates, which is an important thing for a carbon capture system to do. Currently, carbon capture and sequestration, as you mentioned, quotes in the 20% for the CC portion of carbon capture and sequestration, but for the sequestration part, it can get to be over 45%. Our first plant that is being built in San Antonio, Texas, is designed to achieve a 40% energy penalty, just under the competing CCS amine technology. But with fundamental improvements and other research that we have underway, we have demonstrated in laboratory abilities to drive that below 20%.
With the amine technology that you mentioned as well, you're actually left with some quite nasty toxic chemicals, and you've got to obviously purify the amines in the first place. I guess one of the real advantages to this is that the products you're left with, not only is there a market for them, but also they're quite benign.
Benign indeed. In the Earth's history, some 4 billion years ago, a tremendous amount of limestone and other minerals were created from what was at that time a predominantly carbon dioxide atmosphere. And as you likewise mentioned, that mineral sequestration is going on around us all everywhere. Here in Travis County, Texas, there's some 450 pentillion tons of limestone that were once part of the atmosphere of the Earth.
Pentillion, that's unimaginable.
It's a word you don't get to use in casual conversation.
Well, that sort of brings me on to how scalable is this? I mean, is there something where you could put it on any coal-fired power plant in the world at the moment, or are we still looking at a fairly small scale?
It is capable. The plant that we're building in San Antonio, the capital SkyMine plant, will be manufacturing 75,000 metric tons of CO2. Scale is important because in the United States we emit some 2.6 billion metric tons a year of carbon dioxide. In theory, the plants can be scaled effectively infinitely. There's far more salt, water, and room for minerals than there is carbon in the earth to burn.
One of the complaints about green technologies, about technologies that capture carbon quite often, is that it's not economically viable. Obviously, you found an excellent way around that. But in the future, let's say we do have a SkyMine on every power plant and we're producing large quantities of these products. What happens if the market becomes completely flooded?
Well, given the scale of the carbon emissions that we have, that would indeed occur. At that point, you would then be able to operate the plant simply for the purpose of sequestering CO2 and lay aside the minerals, or in the case of the example from your earlier interview, we could put the minerals back down inside a stripped coal seam for the purpose of sequestering it there. But at that point, you then cross into cost. Right now, the U.S. Department of Energy estimates that amine sequestration costs between $100 and $300 per ton to capture it that way. We estimate that we can arrive at a $25 to $50 range for that incremental cost passed beyond markets.
That's the remarkable difference, isn't it? And this sounds like fantastic technology. What sort of timescale are we looking at before we'll see this turning up in different power plants?
Our first large-scale commercial plant, we've been running pilot plants here in Texas for the last 6 years. The first large-scale one will go online in 2013, and thereafter it can be replicated worldwide. And we can be making a dent in carbon certainly inside the next 10 years.
Well, that's very good news. I'm glad that we have these technologies to be optimistic about. Thank you ever so much for joining us. That's Joe Jones. He's President and CEO of Skyonic over in Texas. And you are listening to The Naked Scientists with Ben Valsler and Dave Ansell.
Earlier this week, I met Mira at Cambridge's Museum of Technology to explore the engineering of an iconic bit of coal-fired power, the steam engine.
This week, Dave and I are aboard a Foden steam wagon chugging around the Museum of Technology here in Cambridge. Now, it is a scaled-down model of a wagon, and this site is the old sewage pumping station in Cambridge. Now, Dave, why have you brought me here?
Well, steam engines, historically, are one of the most important pieces of technology. They took us from an economy which is entirely based on animals and stuff you grow off the ground to basically the modern world. And even today, they produce over 70% of the energy which we use in this country.
And well, joining us this week aboard the wagon, or in fact driving it, is the main engine driver here at the Museum of Technology, David Gates. Now, David, how exactly, I guess, are we moving along? So how does a steam engine work?
Well, you take your fuel source, in this case it's coal, which is burnt and heats the water to create steam, which then operates the pistons to create the motion to move the engine.
Because water is going from a liquid to a gas, it expands hugely. At about 100 degrees C, it's sort of 1,500 times, if you're at higher temperatures, even more. And that huge expansion can be used to drive a mechanism. So from a physicist's point of view, you're just causing water to boil, you're getting a large amount of expansion, then you somehow connect that to the wheels. But the actual engineering practicalities of that are a lot more complicated.
Yeah, I imagine there are many steps involved, David.
There are indeed, yes. And in fact, we have a model here which shows those various steps.
So we've come inside to the model now, and in fact this represents a Headley steam engine, which is located here just behind us. It's a cross-section, so we can see what's really going on inside. There is a cylinder towards the back of the steam engine then, into which the steam enters. So there's a tube coming out and a valve on top. So what's really happening here to control the movement of steam into this?
Well, your valve on top allows the steam to go into one end of the cylinder, which will then push the piston inside until it gets to the end, when the valve on top will change direction. This will allow steam to go into the other end of the cylinder and push the piston in the opposite direction.
So there's more pressure on the side of the piston where the steam's coming in than on the other side. So it means overall force on the piston, which pushes it along. And then the piston is attached by a series of linkages to the wheel, which is actually doing the work.
OK, well, we can actually turn this model on then to see the piston movement in action.
The piston is then attached to a long rod, which is then connected to a crank, allowing it to turn a wheel. This wheel must then be somehow attached back to the valve, so as it can be opening and closing at the right time.
Yes, there is known as an eccentric, which is basically a cam off-centre, which changes the direction of the valve.
It's all a very smooth motion, and the wheel is just continuously turning here.
That's correct, yes. You have to have rather a large flywheel in a simple engine like this one, just to create the motion required, keep up the momentum.
I guess the other problem you've got, you can get steam into the cylinder, but where does it go once it's in there?
With this particular engine, when the steam comes out of the cylinder, it just passes to atmosphere and complete waste. Later engines use the steam more than once.
So we've now entered a very large room with two extremely impressive engines here. So these are the main sewage pumping engines here on the site. And I mean, just firstly, from the cylinder down to where the flywheel is, it's about 11 metres in length, this engine, and the flywheel itself is about 7 foot high. It's very grand, David.
These engines were built in 1894 by Haythorne Davy of Leeds, and they have two cylinders on these.
This is where the whole fact that steam is being used twice really comes in.
Yes, when steam leaves the small high-pressure cylinder, there's a lot of useful energy in it, so it's used a second time in the low-pressure cylinder.
And so because the steam has already expanded maybe by a factor of 2 or 3 in the small cylinder, it's going to be a lot bigger, so it's going to take a lot more space, so you need a bigger cylinder to let it expand again a second time and get some more useful work out of it.
What's the benefit of letting it expand again?
Well, essentially, you've still got steam under quite a lot of pressure coming out of the first cylinder because you can't let it expand all the way to atmospheric pressure. The cylinder would be immense and it'd be very expensive to build the engine. And so you can use a second cylinder to let that expand again and get more of the energy out of it, which means you get more work for the same amount of fuel.
So these two processes of expansion are all still basically working, though, to push the piston, David?
That's right, yes. You have a piston in each cylinder, but they're connected to the same rod, which operates the pumps.
And well, another way to get even more energy out of the steam, I guess, is to use a condenser, which this engine also uses.
That's right. When the steam leaves the low-pressure cylinder, there's still a lot of useful energy there. So it's passed into a condenser, where the steam is then turned into water to be used for feeding the boiler, but also it creates a vacuum. So it's actually sucking the piston along as well as it being pushed, so we get more efficiency.
So again, you're getting more pressure difference across the piston, so you're getting more work. So the whole thing, again, you get more energy for free, essentially.
And what about the amount of, say, energy being consumed, so perhaps the amount of coal being burned and so on?
Well, with the way we operate these engines at present, we will burn round about 3/4 of a tonne of coke per day.
So that's equivalent to hundreds of litres of petrol you're burning just to run an 80 horsepower engine for maybe 3 hours in the day. So the efficiencies are nothing like even a modern car.
Steam engines, really, one of the reasons they went out of use was low efficiency.
They really did change industry a great deal, though. So we've seen it in motion, say, for a wagon. It's used here for pumping in the sewage plant. As they developed, they had more and more applications.
Oh, indeed, yes. It really was the steam engine that turned the world round. With spinning mills as well, we could create virtually anything you wanted.
And in fact, even today, most of the electricity you use at home is generated using steam engines, not reciprocating engines like this, but a steam turbine. They basically work by blowing steam past a load of vanes, essentially very specifically designed windmills. They spin incredibly fast, and you get a huge power density from your steam engine, allowing coal power stations, nuclear power stations, oil power stations all to produce lots of steam, generate electricity from it, which you use every time you turn on a light switch.
So essentially, although people think steam is old technology, it still powers the modern world that we live in.
That was David Gates, the main engine driver at the Cambridge Museum of Technology.
And this is The Naked Scientist, with me, Ben Valsler, and with Dave Ansell. We're joined by Professor Dermot Roddy from Newcastle University and Joe Jones from Skyonic. And we've had a few very nice questions in from the listeners. Mikey213 on Twitter has asked us why syn fuels are cleaner than traditional fuels and why they aren't used more. Professor Roddy, I think this is probably one for you.
Yes, well, they're cleaner because your starting point is essentially pure hydrogen and carbon monoxide. So you've got no sulphur in there. As long as you've blown your gasification with oxygen rather than air, you've got no nitrogen in there to give you oxides of nitrogen. So you really ought to be able to synthesise a designer fuel, which is effectively what you do. It can be a diesel-type fuel, a petrol-type fuel, an equivalent of jet kerosene for aircraft. And ultimately, the car companies would like to migrate towards an engine that's a combination of a spark ignition engine and a compression ignition engine, and they'll specify exactly what properties they want the fuel to have, and we can make that.
So by spark and ignition, the petrol engines are spark, but
yes,
compression is diesel.
Is compression engine, and they would like to get away from that situation where you have to make two types of engine for two types of vehicle, and just make one fuel that has the advantages of both, and they'll specify exactly how they want that fuel to perform, and we synthesise that.
Fantastic. Coming back to you, Joe, we have a question from Pekka Oilinki, and she got in touch on Facebook. That's at thenakedscientist.com/Facebook. And she wants to know if there's any way that you can mimic nature and produce a sort of recycled oil. If you can make a new fuel by taking the CO2 out from your waste.
Well, taking CO2 and reconverting it into fuel, CO2 itself is completely spent fuel, so one has to add energy to go back up the thermodynamic curve from carbon dioxide to a usable fuel. And the most efficient chemistry for doing so is photosynthesis, that is an intricate process that adds energy from sunlight. Nothing else that man has done on a pathway has approached the efficiency of photosynthesis. At Skyonic, we've been working with the University of Texas at Austin researchers who are working on bioalgal fuels made from bioalgae. And we've been feeding it with bicarbonate of soda manufactured from our SkyMine process, and they've reported very good results. 90% incorporation of the CO2 and a tripling of the growth rate because it actually creates an algae bloom. It also throws some of the biologic triggers inside the algae that make it produce oil preponderantly compared to plant matter.
So we can't mimic nature yet, but we can, of course, get nature to do that work for us.
We can hitch a ride on nature at this point, and it's producing it's probably the most promising means for making fuel directly from CO2.
Excellent.
Got another question here, probably for Professor Roddy again. This is from Jeremiah. He asks, how can coal be converted to petrol? I guess you've already covered the first half of this by making the syngas. What do you do with the syngas to make something like petrol?
Well, the South Africans have been doing this for a very long time because of the years of sanctions. And so the well-known technology is called Fischer-Tropsch technology, and that can be used to synthesise hydrocarbon chains. Traditionally, the process was used for synthesising diesel, but you can synthesise a naphtha-type material if you want to, or a kerosene-type material. It's just a question of optimising the reaction conditions and choosing the right catalyst. So people are starting to develop a range of fuels now from synthesis gas.
Brilliant. Another question actually here from Bimal Raul. He asks, are there any issues with this underground coal gasification, such as poisoning of groundwater? Can any of the byproducts from underground get up to the surface in a negative way?
Well, it's very important to do it at depths where all of the water has been formally classified as permanently unusable. These are very, very salty water deposits at depths of a kilometre or thereabouts. Nobody would ever abstract those kind of waters. The very fact that they're heavily salty means they're poisonous anyway. And so you have to be operating at the kind of depths where nobody would ever bring that water to the surface as a water supply. Then no matter what happens, you're not going to cause contamination that causes any problems.
Thank you very much. And Joe, I wonder if we could come to you for one very quick answer. Doug Throp has written in to say that we know that we use catalytic converters to get rid of the rubbish in our petrol fumes. Why don't we do that with coal-fired plants?
Well, catalysts generally don't change chemistry. They only drive it at accelerated speeds to the same ends. And when a power plant operates perfectly, it does achieve complete combustion. So a catalytic converter may be good for making carbon monoxide into truly carbon dioxide. It's still carbon dioxide at the end of it. So you can't clean up that fashion. You can only change it from a gaseous form into a mineralized form or into some other form. You have to change state.
Well, thank you very much. That was Joe Jones. Before him, Dermot Roddy. Thank you ever so much for joining us on the show. Dave.
And now we join Diana O'Carroll with our question of the week.
This week, time to sort the clutter in the genetic attic.
My name is Alan, and I'd like to know what the point is of non-coding DNA.
There are strings of letters and proteins that seemingly don't code for anything in particular. So does all that extra stuff have a purpose?
I'm Julian Huppert. I'm the Member of Parliament for Cambridge, but before that I was an academic working on genomics. Well, there are various ways of thinking about it, and we're still trying to understand some of it. But in some ways, the coding sections are the recipes for the proteins that we have, the genes. And the non-coding DNA is very important in saying how much of this should be there, when is it turned on, when is it turned off. So all of those controls are hidden in the non-coding sections of DNA. Then there are some other bits which are old things which we don't really use, genes which were useful a few million years ago. We still have bits lying around. And then there are some bits which really are junk, that are viruses that have crept into our genome over time. What I used to work on was something called the G quadruplex. So DNA of the right sequence can form 4-stranded knots. And these can act as off switches, which stop a gene from being active. And it started off as an interesting theoretical curiosity. We actually found that almost half of all human genes seem to have these switches in a way that could be playing a role in turning them on and off. And in particular, most cancer genes had these little structures which just almost formed a little knot at the beginning of the gene to make it marked as off.
So-called junk DNA can be acting in other ways, as on-off switches, packaging for coding DNA, or instructions on how that DNA is unpacked. And Imat Fal said on the forum that DNA can have another use altogether, fingerprinting for identification. Next week, what's the point of duplication?
Hi, I'm Rebecca Ferris. I live in Norwich, and I was just wondering, why is it that we have 2 of some organs, like we have 2 eyes and 2 kidneys, when we could probably make do with just 1, but we only have 1 of some other organs? If we're going to have a spare kidney, why don't we have a spare liver And could it change as we evolve? If we don't really need these things, could we lose them, or could we get an extra one of some other organs? Thank you.
Why have 2 kidneys when we can get by on 1? Answers to chris@thenakedscientist.com. You can write on the forum at thenakedscientist.com/forum. You can Facebook us or Twitter @NakedScientists.
That was Diana O'Carroll with our question of the week. And if you know why we have spare organs, get in touch.
But that's all we have time for this week. Thanks very much to our guests, Dermot Roddy and Joe Jones, and our production team of Tom Simpkins, Mira Senthalingam and Diana O'Carroll. Next week, we're pushing through the pain barrier. We'll find out how chronic pain is managed, and we'll explore the new research into blocking problem pain permanently. So if you've got any science questions for us, tweet them to @NakedScientists, write on our wall at thenakedscientist.com/Facebook, or email us chris@thenakedscientists.com.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the Natural Environment Research Council and UK FAST. For more information, look us up online at thenakedscientists.com.